Today we are going to talk about another topic. It's called vectors and matrices. It's linear algebra, okay? So we will also use the concepts of vectors and matrices to find the solution of your differential equation. So first, let's just quickly review what vectors are. So a vector means the vector contains the magnitude and also a direction. In your first year, when you studied statistics, for the statistics, we learned that velocity, acceleration, force are vectors because it contains a magnitude and a direction. For example, like a velocity, acceleration, and the force. So if you express a vector, it should always contain one, or people should know the magnitude and also their direction. Okay, so like the magnitude, this is just the magnitude. But if I give an arrow, then I have a direction. So the force could be going up, or in that way here, that would be a vector. Then the norm, we say that the magnitude, and sometimes we say it is a norm. The norm of a vector is that, suppose this is a vector, I have three components. For the three components, the magnitude or the norm, we have double bars. Okay, that will be the square root of the summation of each component square. For example, if I have a vector -1, 4, 1, and maybe the direction is here, then this magnitude is square root of 18. Okay, that's how you find the norm. And here we have some properties of the norm. Okay, if I have a scalar alpha, the scalar multiplication, I can also separate the scalar and the vector. Okay, find their magnitude or norm together and then times together. So this is scalar multiplication. And for this scalar, well, if I have a vector, then I use norm to find the magnitude. If this is a scalar, not a vector, I only need the like a determinant or just like a magnitude, absolute value, okay, 1 bar. If alpha is greater than 0, this is f, and if I times alpha f, alpha is greater than 0, then I have this new vector in the same direction. If alpha is negative, like -2f, then we will do the opposite way. Okay. So same direction when alpha is greater than 0. When alpha is negative, then it is in opposite way, opposite direction. Next, when we say that the norm of a vector is 0, What does that mean? That this norm is 0 only when, because we need to find the square root of the summation of each component square. That means A should be 0, B should be 0, C should be 0. Then only if and only if this vector is a 0 vector. You can see this is a scalar 0, okay, because it is a magnitude, find the norm. But this one is a vector, okay, it is a 0 vector. So only when the vector is a 0 vector, then the norm is 0. Okay. Next one, the product of a scalar and a vector. If I have a vector f, I have 3 components. It is in R3. Okay. Then I have a scalar alpha. So when I have alpha times this vector, each component will also multiply alpha. Okay. If I have 2 vectors f and g, I want to do the sum of these 2 vectors. Then the sum of these 2 vectors is, see the component, they also sum of their component. Okay, so A1 corresponding this, the first element, they will add them to they will add together. The second component, they will also add together. And the third component, they will add together. Here is the algebra of vectors. If I have 2 vectors doing the sum, if I switch the order, it is still the same. This is called commutative law. So they can commute. The second one, if I have 3 vectors, I'm doing the sum of these 3 vectors. You can either take the first 2 to have a summation first, or the last 2 do the summation first. This is called associative law. If I have a vector plus a 0 vector, it doesn't change anything. Okay, 0 vector does not affect the your vector f. So the answer is still f. If I times a scalar alpha to the sum of these 2 vectors, that is also equal to the product of the norm individually, then do the summation. Okay. And if I have 2 scalars, alpha and beta, well, you can think about the beta first, doing the scalar, doing this multiplication of your vector first, and then times another scalar. You can also switch. Okay, beta, alpha, f. If I have 2 scalars times 1 vector, okay, then you can also separate these 2 scalars times the vector first and then do the summation. Okay. Next one, triangle inequality. Okay, so how do I express this math? This is the norm of a sum. Norm of a sum. And here is the sum of the norm of the individual vectors. sum of the norms of the individual vectors So let's draw this. Suppose I have a f. This is f. And then here is a g. First, what is the vector f plus g? You can use the triangle method. Your f plus g is this is f plus g. So you can see the norm will be the magnitude. This is the norm of a sum. This is the sum of the norms of individual vectors f and g. So this is always bigger than or equal to f, the norm of the sum. Okay. Next, what is the unit vector? If you see that unit vector, what things come out from your mind? If you see unit vector, since it is unit, then the magnitude should be 1. So what is a unit vector? For example, in our Cartesian axis, I say I is 1, 0, 0, or J is 0, 1, 0, K is 0, 0, 1. First, let's just see this I vector. What is the norm? The norm will be 1 squared plus 0 squared plus 0 squared. So it's 1. So it is a unit vector. Same thing applies to J and K. They are unit vector. And then, since they are unit vector, I can express f, this vector. If I have something in their components a, b, c rather than 0, then I can use the unit vector to express the doing the linear combination of the unit vector to express the vector f. And if f is not unit vector, then I can also create a unit vector for f, as long as I divide the norm. So if the vector, you can see that if it is a vector, we have underscore, underbar. Later on, when we talk about the matrix, we have double underbars. So this is a vector. Divide by the norm. Then this is also the unit vector. And this unit vector is in the direction of the vector f. In the same direction So suppose if I have a vector f, then I divide by the magnitude, then maybe this will be f divided by the magnitude. This is the unit vector, and the direction, since a vector, I need a magnitude and the direction. The direction is in the same direction as your vector f. You see this? This is a norm, so it is a value. But f is still a vector. Right? So this is still a vector. Okay? And since it is a vector, I should have a magnitude and also the direction. So you see the f, this new vector, I still have the same direction as f. And the magnitude will be 1. So if I have another vector v, v is in the direction of f. And we say this v because a vector, I need the direction and also the magnitude. So here I say that with length 10. How do I describe v? Then the v will be 10 times the unit vector in the f direction. So suppose this is f, and we know the unit vector here is f divided by the magnitude. This is unit vector. And now I have another vector v. It is still in the same direction of f, but I have the length is 10, so maybe the v is here. Okay, same direction. And then the magnitude is 10. 10 of this unit vector. So you have like, so it should be like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then this is your v. All right. Next, I think that you know what is dot product. Okay, for the dot product, the result will be a scalar. If I have a vector f and vector g, two vectors, if I do the dot product, what does that mean, dot product? The first element will times the first element of each vector. I have a1 and a2. And I times I dot I will be 1. Because I dot I, 1 times 1, there will be 1. Others will be all zeros. So here's the example. These two vectors, if I do the dot product, I dot I will get minus 2 square root of 3 plus 24 minus 3 pi. Okay, and you see that this is a scalar, not a vector. So here are some properties of the dot product. F dot G, I can also switch these two. Again, that the order doesn't matter. Okay, this is called commutative. Commutative. Second one, if I do the sum of the vectors first and do the dot product with another vector, then I can do the dot product with that vector first and then do the summation. This is distributive. if I have a scalar, this scalar can go to the first vector or the second vector, doesn't matter. If I have the same vector doing the dot product, then there will be the norm square. Remember, this is a norm, and that's norm square. Remember that suppose f is a, b, c. What is the norm of f? Square root of a squared plus b squared plus c squared, right? Then f dot f a, b, c dot a, b, c. I have a squared plus b squared plus c squared. So this is just equal to the norm square, right? Then I know that if you dot yourself, you get the norm square. But if the norm square is 0, what does that mean? F dot f, the same vector, and after doing the dot product, I have a 0, and it is a scalar. That means only when the f, this vector, is 0. Okay, because norm square. If you have norm square and it is 0, that means the norm should be 0. And when the norm is 0, we just say that in the beginning of this chapter, if the norm is 0, if only if the vector is a 0 vector. So now let's see this example for f dot g. Suppose I have f and I have a g and here I have an angle theta. So f dot g is the norm of f times the norm of g, cosine times cosine theta. So suppose I have two vectors f and g. I want to find the theta between these two vectors. How do I find this theta? Okay, we have a cosine. So the angle theta between the vector f and the vector g, that will be cosine theta equal to first inner product or the dot product divided by the norm, the product of the norm. So here I have minus 1 times, I don't have I component, that means that's 0. And the second component, for j component, I have a 3 times times 2. And for k, there will be 1 times minus 4. Here is minus 1 squared, the norm, so sum of all the components square. Here we have 2 square plus 1 square, oh no, minus 4 square. I get 2 over square root 2 of 220. So you can get the theta. Theta is around 1.436 radius. Okay. Any questions for this one? Next, we are going to talk about the Cauchy-Schwarz inequality. So for the Cauchy-Schwarz inequality, here is the expression. First, let's see the left-hand side. What is this? You see, I have like 1 bar. So it is like an absolute value. Because inside this absolute value, it is a scalar, right? So this is the magnitude of the dot product of 2 vectors. Magnitude of dot product of 2 vectors. And the right hand side, that'll be the magnitude of the product of the norm of these 2 vectors. So magnitude of product of the norm of the vectors. So let's prove this. And to prove that, because they use the dot product, and remember that when you do the dot product, that means I have 2 vectors and with the angle theta. Okay, and for this angle theta, we express that cosine. Okay. So, because here I have a cosine between these 2 vectors. So think about the cosine. We have a values for the cosine. Or we can say we have a boundary for the cosine. It is between -1 and 1. So cosine theta is between -1 and 1. And what is cosine? 2 vectors doing the dot product divided by the magnitude of the product of these 2 vectors. So, and since it is a magnitude, okay, it is always greater than 0. So I can just times this magnitude of the product. Then we have minus f times the magnitude of g. The right hand side is also the norm of f times the norm of g. And that's why here. Alright, any questions about the proof? The next, we are going to talk about the cross product. The dot product after you have a dot product, you get a scalar. For the cross product, you will still get a vector. So here you can put like a vector. If I have two vectors, when we do the cross product, then this is a result. And for this result, first we need to green. This is the determinant. Okay, and you should know that how to calculate this determinant, right? Choose one row and one vector. Do the decomposition. Like here, I have I times the determinant, j times the determinant plus the negative sign, and then k times the determinant, same sign. All right. And if you switch the order, now the order matters. If you switch, then I should get a minus sign here. Because if I change the determinants, especially change two rows, then they will change the they will cause us a change sign. Okay. We will also talk about this more when we talk about the matrix. But I think that you learned this in your junior or senior high, right? No. Here are some properties of the cross product. The first is that if you switch the order, then I will cause a sign change. And if f and g, these two vectors, are orthogonal, no, I mean the result, this result is orthogonal to f and g. If I have a f and here's a g, when I do the cross product, I will create the third vector, and this third vector is perpendicular to those two original vectors. It is called orthogonal. Orthogonal means like 90 degrees. Okay. And suppose f is not a zero vector. G is not a zero vector. Then what happens if f cross g is 0? Then we also get this result, f cross g is 0 if and only if f and g are parallel. So vector f and g are parallel. So that if f is here, g is here, they cannot create one vector that is perpendicular to f or to g. Because when they do the cross product, it is a zero vector. Now, if I do the cross product with a sum of two vectors, I can do the cross product first by each and then sum them together. If I have a scalar alpha, you can think about this alpha belongs to f or belongs to g. And then let's see the magnitude or the norm square of the cross product. We know that the the dot product, I will get the multiplication, the magnitude of the product of the magnitude times cosine theta. And then this one, because I take the magnitude, the norm, so finally it should be a scalar. Okay, so this one equals the norm square, the product of the norm squares minus the dot product square. And we can also simplify it. It is f square, the norm of g square, then the dot product, that's f g cosine square theta. And it should be 1 minus cosine square theta. So the result will be the product of the norm squares, the norm square times sine theta, sine square theta. And we say that the cross product, the result of the cross product is a normal vector. The normal vector, that means the normal vector is orthogonal or perpendicular to the vector f and g. So if I have f, suppose I have a g here. This is g. Here's f. Then I have the normal vector n. N could be so it is orthogonal to both vectors, and f cross g the magnitude, actually the norm of the cross product is the area of the parallelogram. Okay, so suppose this is G and here is F. Here's the theta. So this is equal to the product of the two norms times sine theta. Okay, because if I have a square, then I have a square here, right? So if I take the square out, then the product of the norm times sine theta. Right, next, the volume of the parallelepiped is here. You do the cross product and then inner product, the dot product, and then take the magnitude. So if I have vector g, here's the vector g. And this is vector f. then F cross G. Suppose this is F cross G. And F and G, F cross G, then I have an area So suppose I have H. This is a vector H. Well, let's take a break first. Okay, you can take a break and then let me finish this. Alright, so now let's continue. Next, we are going to talk about the vector space. What is the vector space? And also the vector space R to the n. So let's consider the norm of an n vector. Okay, this n vector is not an n vectors. Okay, I have an n components. For these n components, the norm, again, the norm will be the square root of the sum of the component square, individual component squares. Okay. And for the vector space, that should satisfy the algebra of vectors and also the properties of the dot product and also the Cauchy-Schwarz inequality. So if I have n components in my vector, then the unit vector is again that the vector divided by the magnitude, by its magnitude or its norm. Always, when you see the unit vector, that means once you have a vector f, divide by your magnitude or divide by your norm, this vector becomes a unit vector. Okay. Because it normalizes it. Then what is the subspace of the n space? The subspace we say that there's a set S. The set of S of the n vectors is called the subspace. First, zero vector has to be in the set of S. And the sum of two vectors should be also in S. The product of any vector in S is with any scalar in S. For these two, what does that mean? That these two, the second and third, that means alpha times the vector f and beta times the vector g. And I add these two together, it should be still in the set S. Let's see some examples, then you know that what subspace is. First, we say that S consists of all vectors in n dimension, and the norm is 1. Then we say S is not the subspace of R to the n. a subspace of the R to the n, I should satisfy at least the first 0 should be in S. Sum of two vectors should be in S. And the product of any vectors in S is with any scalar in S. So we also need to check this criteria. First is 0 in S. We say that S contains all vectors in R to the n. So first, 0 is 0 vector in S or not? We say that S contains all vectors having norm 1. I need norm 1. Okay, so 0 vector, what is the norm of a 0 vector? The norm of a 0 vector is 0, right? So it is not norm 1. So 0 vector is not in S. Okay. Any questions for this? Second, S, I should have all the vectors with norm 1 in S. However, 0 vector, the norm of 0 vector is 0. It's not 1. So 0 is not in S. Let's see another one. A sum of two vectors having norm 1. Will that be also in S? A sum of two vectors having norm 1. Will not actually have norm 1. For example, if I have a vector A that's 1, 0, 0, we have norm 1, right? And then B, that's 1 over square root of 2. We do more. Let's see. Have 1, 0, 0, 0. 1 over square root of 2, 0. 1 over square root of 2, 0. This is also with norm 1, right? Because the square plus the square, that should be 1 over 1. So the norm is also 1. But A plus B, this two vector, with the norm, this norm is square root of 2. This norm is now 1. Okay. So next, if my vector is 1 over square root of 2, 1 over square root of 2, 0, 1 over square root of 2, 0. But if I times a scalar, then it should be alpha 1 over square root of 2, 1 over square root of 2, 0. Then this norm, it should be 1, right? Because we said that we have a space that contains these three, or in this equation, in this question, I should have a S with norm 1. All the vectors should have norm 1. But in that case, this norm is alpha, not 1. So they violate all three requirements. So S is not in, this S is not a subspace of R to the N. You can define the S. Okay, this is your definition of your S. And then we may ask that, is this S a subspace of the N dimension? Apparently it is not. Okay, no, because they cannot satisfy these three criteria.
Professor, can you explain more about the third point?
Oh, this, the norm of F is 1, right? So it is still satisfy our assumption because we said that S should have a norm 1. But from the third criteria, if I times any scalar with this vector, finally this is still a vector. And this vector should be also in our S. It should be. But actually, if I times alpha, the norm is alpha rather than 1. So this is not in S. So once you times a scalar, it is not in S. Then S, we cannot say that S is a subspace. They should satisfy these three. It's a little bit tricky. And now for this topic, later on, especially when we talk about the metrics, you should have a clear mind in class to think about some theoretical statement. Okay, because you need to use your noodles a lot now. Let's see another example, then you will be familiar with this concept. Suppose now I say that the M are all vectors in R5. Dimension is 5. And then here is the condition. The first component is an even number, even integer. Then I want to know that if M is a subspace of R5, that's the question. If I define this set M with this condition, the first component is an even integer, then M is a subspace of R5. We also need to check 0. Okay, first 0 should be in the M. Okay, so the first component is an even integer. 0 vector the first component is even. Okay, 0 is an even integer. So the first one is correct. So 0 is in the set M. Second one, a sum of two vectors in M is in M. Correct? Here, the M, I need this condition. The first component is an even integer. Even plus even, 2 plus 4, 6 plus 8, it is still even, right? You cannot say that 3 plus 4 or 3 plus 3, because if it is 3, then your first component is not an even integer. So your first component, I don't care the rest, the first one should be 0, 2, 4, 6, 8, 10, and so on. And no matter which two I choose to do the summation, it is still an even number. Okay, even integer. So a sum of two vectors in the set M is still in M. The third one, if I times a scalar and see if after timing the scalar that vector is still in M. So if I have a vector A, suppose the first component should be an even integer, so like -4, and the rest, whatever, I can even put like a pi. Then if I times the scalar, like 1/4, the scalar is 1/4 times A. This becomes -1 square root of 2 divided by 4, 1/4, -1/4, and pi over 4. And you can see that this -1 is not an even integer. So M is not a subspace of R5. Okay. Any questions for this example? Next example. If my set S just contain a zero vector, then S is a subspace of Rn. Is that true or false? If my set is just like a zero vector in Rn, so I have n terms, is this S a subspace of Rn? R to the n. First is the zero vector in S. Yes, this is the zero vector. And sum of the two vectors should be also in S should be also in S. I only have this vector. So zero vector plus zero vector is still a zero vector. And any scalar times a zero vector is still a zero vector. So it is true, and this is just a trivial subspace. Okay. Well, in your term, okay, you can try that. S contains all vectors in this form in R2. And then is S the subspace of R2? Try to verify that using these three criteria. Okay, let me give you 3 minutes. So first, is 0 in the space in S? Yes, because if I put x is 0, then I have a 0, 0. So 0 is in S. And how about the second one? Two vectors. If I sum of two vectors, so first vector I say A, 5A, and the second vector B, 5B. Then what is the result? A plus B, 5A plus 5B. Is this vector also in S? Yes? No? You see that this should be A plus B and 5 times A plus B. Right? In that case, you can see that this is like X. This is X. So it is in S. Okay? How about the third one? If I times a scalar, if I times a scalar to the vector A, 5A, then what do we have? Alpha A, 5 alpha A. Is that in S? Yes, because alpha A, you think this is an X, 5 times alpha A. So this is X, and here's X. So if you define a set with this condition, then we say that this S is a subspace of R2. Okay, any questions for this one? If you take the linear algebra later on in electrical engineering department, you will talk more about this space concept. But here, I think that's enough for you to understand. Next one, we are going to talk about the linear combination of many vectors. Here we say n vectors. So if I have k vectors in Rn, what is the linear combination of these k vectors? A linear combination means that for each vector, I will multiply a scalar Cj. Okay, so C1, C2, C3 to Ck. This is the linear combination of n vectors. And we say that the set of all linear combinations is the span of these vectors. So the linear combinations span these vectors. These vectors is here, f1 to fk. Next one is the linear dependence and linear independence of n vectors. What is linear dependence? We say that f1 to fk are linear dependent if and only if one of the vectors can be expressed as a linear combination of others. For example, I have a f1, f2, f3, f4. These four vectors, if we say that these four vectors are linear dependent, that means one of the vectors can be expressed by other three vectors. If I cannot find that, they will be called linear independent. Okay. So if it is not linear dependent, there will be linear independent. But how do I know that? How do I check or test those vectors are linear dependent or linear independent? Because we need to know that later on when we find a solution, we need independent ones. So to check if those vectors are linear independent, we have these two criteria. We say that f1 to fk are linear dependent if we express the linear combination of these k vectors equals 0, but those scalars are not all zeros. I may have like 2, 4, 3, 5, 6, whatever. If the coefficients are not all zeros, then one of the vectors can be expressed by the rest. I didn't change it here. It should be alpha 1. For example, because if they are not all zeros, and if A1 is not 0, then I can divide it by A1. Okay, so here I divide by A1. I divide by alpha 1. Then I can have F1, this vector, be minus alpha 2 over alpha 1 F2. And then here's alpha k divided by alpha 1. You see, one vector is the linear combination of the rest of the vectors. Then this is not linear independent. So for linear independent, if and only if those coefficients are all zeros. Okay, I cannot find one vector as a linear combination of all others. Alpha 1 equals alpha 2 equals alpha 3 to alpha k. They are all 0. For example, here in R4, I have F1, F2, and F3. Are they linear independent or linear dependent? Let's see. We always need to check. First, to have a linear combination of these three vectors, alpha 1, F1, plus alpha 2, F2, plus alpha 3, F3. That's a 0 vector. We need to check those coefficients, okay, to see if they are all zeros or not. So we can substitute F1, F2, and F3, these three vectors. We have alpha 1, alpha 2 plus 2 alpha 3, 3 alpha 1 minus 6 alpha 2 plus alpha 3, and alpha 2 minus alpha 3. This should be right hand side 0 vector, so 0, 0, 0, 0. Then you can compare. Alpha 1 should be 0. Alpha 2 plus 2 alpha 3 should be 0. And here 0. Alpha 2 minus alpha 3 should be 0. So alpha 1 should be 0. Alpha 2 plus 2 alpha 3 should be 0. 3 alpha 1 minus 6 alpha 2 plus alpha 3 should be 0. Alpha 2 minus alpha 3 should be 0. And then we get alpha 1 and alpha 2 and alpha 3 are all zeros. That means they are linearly independent. Alright, then your time, check if F1, 2, That's why do I have a 4? That's fine. 1, 2, and 3. To see if they are independent, linear independent, or linear dependent. Let's just change that to 3. Dependent or independent? To check that, we need the coefficients alpha 1, f1 plus alpha 2, f2 plus alpha 3, f3. And it should be a 0 vector. Now compare the coefficients. Alpha 1 plus 4 alpha 2 plus 2 alpha 3. And then the second component will be minus 4 alpha 1 plus 5 alpha 2 minus 6 alpha 3. It should be 0, 0. Now we can compare the coefficients and then here. So we have alpha 1 plus 4 alpha 2 plus 2 alpha 3 should be 0. And minus 4 alpha 1 plus 5 alpha 2 minus 6 alpha 3 should be 0. How do you get? Alpha 1 is minus 34 divided by 11 by 41 alpha 2 and no alpha 3, and alpha 2 is minus 12 divided by 41 alpha 3. So we can choose alpha 3 be minus 41. Then we have 34 f1 plus 12 f2, that's 41 f3. So you can see that f3 can be expressed by the linear combination of f1 and f2. So they are linear dependent. So f1, f2, f3 are linear dependent. So here's a note. If you contain 0 vector in your set, then it will be linear dependent, because if you have a 0 vector, so you should have a 0 vector, then plus, even though you have all coefficients 0, here you have f1, f2, f3, fk. Okay, I can have 0. So those coefficients are all 0. But for the 0 vector, I can have the coefficient 1, 2, 3, any number. So the coefficients are not all zeros, then they are linearly dependent. Okay. Unless you have all zeros, then we say that this is a linear independent. But here, the coefficient, I can choose any number, not 0. So if you have a 0 in your set, then they are always linearly dependent. Okay. Next one. Let's see what is the basis. This is very important. The basis. The basis for a vector space. We say that S is a subspace of Rn. And then F1 to Fk will form a basis for this S if they have these two criteria. Those vectors are linearly independent. I cannot express one of the vectors by others. And the second one, every vector in this S can be a linear combination of your basis. Okay, that's a definition for the basis. And actually we use the basis a lot that you just didn't know. For example, in statics, okay, a force, I can express this is 3I plus 5J plus 6K. I, J, K are bases. And I use the basis to create another vector. So any other vectors can be expressed by using those three bases. Using these three vectors, and those vectors are called bases. Okay. And then here's a note. The basis is the minimum set of vectors needed to specify the subspace. Okay. Because they are linearly independent, and any other vectors can be expressed by the linear combination of these vectors. So that's the minimum set. And for the standard basis, those are the standard basis. In 2 dimension, we say 1, 0, 0, 1 in R2. Or even in R3. In R3 there will be 1, 0, 0, 0, 1, 0, and 0, 0, 1. That is the standard basis. So here, let's see. We say that F1 and F2 in 3 dimension. This is not the basis. And why it is not a space? It is not a basis. First, we need to check out the coefficients. Okay, so C1 F1 plus C2 F2 is 0 vector. We have C1 1, 2 minus 1 plus C2 0, 3, 1. That's 0, 0, 0. So C1 is 0, and 2C1 plus 3C2 is 0, minus C1 equals C2 plus C2 equals 0. And then for these 3 simultaneous equations, C1 and C2 should be 0. Then at least the first one, F1 and F2, they satisfy the first criteria. F1 and F2 are linear independent. But in R3, we may have 0, 0, 1. For this vector, can I use F1 and F2 to express that? And I cannot find any linear combination by F1 and F2. So they are now the basis. The basis should be all other vectors can be written as a linear combination of these vectors. Apparently here they cannot satisfy, so they are not the basis. Okay, let's see this. I have a set S that consists of all the vectors, and this vectors is in this form. Always 0 in the first and the fourth element. That is in R5. Then we say S. This S is a subspace of R5. And for all the vectors 0, x, y, 0, y, I can rearrange it, put x outside. What do we have? 0, 1, 0, 0, 0. Right. Plus, put y outside. That'll be 0, 0, 1, 0, 1. You can think about this vector in R5. This is F1. And here it is F2. And this is like a linear combination, right? Linear combination of F1 and F2. Then I have a coefficient x and y. So this is linear combination. And F1 and F2. These two vectors are linearly independent. So if the vectors are linearly independent, and every other vector or every vector in S can be written as this linear combination, then we say F1 and F2 are bases or form a basis for this set S. So F1 and F2 form a basis. So here's a note. Basis is not unique. Very important, because probably this statement will be in your true and false. But the basis has the same number of vectors. For example, we know that in R2, 1, 0, 0, 1, that will be the basis, right? But I can also say that 2, 0, 0, 3 will also the basis. Okay, because every vector in R2 can be written as a linear combination of this. And these two are linearly independent, right? Because for the linear combination, C1, 2, 0 plus C2, 0, 3. Those coefficients are scalar. It could be 1/2. This could be 1 third, then I can create 1, 1. Right? Or if this is 0, then I create 1, 0. So the bases are not unique, okay? But the bases, once you say those vectors are the bases, then they are linearly independent. Okay? Any questions for this? Next one. Let's see what is the dimension of a vector space. So the dimension is the number. Okay, dimension is a number. Number of what? Number of vectors in any basis of a subspace of Rn. That is called dimension of that space. So numbers of vectors in the basis of that subspace. For example, in this case, I have two bases, right? The number of vectors in this basis of subspace in Rn, this is in R5. Then what is the dimension? This dimension is the number of vectors, 2, right? I have 2, and these 2 vectors form the basis, so that is 2. And a vector space V, if we say that has n linear independent vectors, then if I have n plus 1 vectors in V, then they will be linearly dependent, because these form the basis. Once these form the basis, the next vector, the other vector, can be expressed or written as the linear combination of your bases. And of course, the n plus 1 vectors will be linearly dependent. For example, if I have 3 linear independent vectors in R3, so it'll be 1, 0, 0, that'll be the basic one. So n plus 1 vector, so this is n, right? N equals 3. N plus 1 vector, if I have the fourth vector, say 2, 3, 1. This vector can be written as a linear combination of the spaces, right? 2 times 3 times 1. And I add these 3 vectors together. So these 4 vectors will be linearly dependent, because this vector can be written as the linear combinations of these 3 bases. So that also means that I have n linearly independent vectors in V. Then these n linearly independent vectors are the bases. Okay? Are we on the same page? Then based on this concept, let's see what is the spanning set. I have n vectors, and these n vectors is just a set of vectors in the vector space V. We say this vector V, a vector V, we call this V is a linear combination of the vectors from V1 to Vn. So V can be expressed as a linear combination of V1 to Vn. And then C1 to Cn are the coefficients. Then we can say that the set of all linear combinations of these vectors is the span by V1 to Vn. Once I have V1 to Vn, there's n linearly independent vectors. Then any linear combination will be the span by this set. Okay, we will see some examples later or next Monday for this. Just remember that if I have a set v1 to vn and another vector v is a linear combination of v1 to vn, then we say that v1 to vn span the vector space. Okay. Next one, let's see the orthogonal and orthonormal set. What is orthogonal set and orthonormal set? First, we say that this set is orthogonal. That means from the vector x1 to xk, they are orthogonal if and only if, well, if any two of these vectors of their dot product will be 0. But each vector is not a 0 vector. Okay, then they call orthogonal, which means they are perpendicular. So x1 is here, x2 is here, and they are orthogonal. So their dot product is 0. But the vector itself, it is not a 0 vector. Okay, and I may have another one. This is x3, and x3 is also perpendicular to x1 and x2. When they do the dot product, they are 0. So if you see two products, a dot product is 0, then we can say that those two vectors are orthogonal. And by the way, that for this future classroom, they have a really strict rules. So every time I get so many emails that say, please tell the students water only. All right, no food, no drinks, no beverages, only water, no tea, no coffee, no even bottled tea, bottled coffee, or whatever, only water. Okay. So we say that two vectors are orthogonal if their dot product is 0, and they are not a 0 vector. Another one is orthonormal rather than orthogonal. So orthonormal means they are also orthogonal, and these vectors are a unit vector. Those vectors are unit vectors. Okay, unit vectors means the norm is 1. If they are orthogonal and the norm is 1, then we call this is an orthonormal set. Okay. So orthonormal means that orthogonal plus unit vector. For example, the standard basis E1 to En. E1 means 1, 0, 0, 0. E2, 0, 1, 0, 0. And the last one will be 1. Okay. This is also called standard basis. Those standard bases are orthonormal because if you take any of two vectors to do the dot product, they'll be 0. And also each vector is the norm of each vector is 1. All right. Oh, so the standard basis is in orthonormal set. In Rn. Next note, if these k vectors are orthogonal, then I times a scalar. Here's a scalar A for these vectors. And also this scalar is non-zero. This set is also orthogonal. For example, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 5. Okay, they are orthogonal, right? But they are not orthonormal because this vector is, the norm of this vector is not 1. So these three are orthogonal. So if I times 3, 3, 0, 0, the second one, I times 6. And the last one, I times 1/5. These three vectors are still orthogonal. Right? The dot product is still 0. But they are still not orthonormal because the norm of this vector and this vector are not 1. Okay, so if you times a scalar, they are still orthogonal. If they are orthogonal, then I divide by my norm. This becomes a unit vector. So overall, this is an orthonormal set. Okay, if I divide by my norm, that is the unit vector, right? 3, 0, 0. If I divide by norm, the norm will be 3. What is this? 1, 0, 0. It is a unit vector. And how about x2? x2 is 0, 5, 0. Then I divide by my norm, which is 5. Then I got 0, 1, 0. So here you can see that the dot product is still 0 and the norm of that vector is 1. So they are orthonormal. Okay. All right. Next, the Pythagoras theory. Now, k vectors are orthogonal, and this is an orthogonal set. Then x1 plus x2, the norm of the sum of the vectors square will be equal to the sum of each individual vector's norms square. We can prove this. First, from the left-hand side, what is the norm square? This is still a vector, right? A vector, the norm square, this is v in the product v, or in v dot product the v. So x1 plus x2 to xk there'll be the dot product, so x1 plus x2 plus x3 to till xk. And then we copy it. Right. So you copy it, what happens? Remember, those vectors are orthogonal. Orthogonal means that the dot product is 0 if you do not dot product yourself. So x1 dot product x2, that'll be 0. But x1 dot x1 itself, that's the norm square. Okay. But if you dot product with other vectors, there will be all 0. So x1 dot x2, 0. x1 dot x3, 0. xk, 0. Only x1. So I have x1 dot x1. Similarly, x2 dot x1, 0, because they are orthogonal. x2 with x2. Okay, we keep it. x2, x3, 0. Others will all be all 0. So I have x2 dot product x2. And then similarly, till xk. While the others will be xi dot product xj, but I is not equal to j. This part, because they are orthogonal, they are all 0. So that's why this is the norm square, some of those norm squares. Okay. So we have a note. Two vectors are orthogonal if and only if their dot product is 0. Okay, not the 0 vector, because when you do the dot product, it should be a scalar. Okay, so it should be a 0. Any questions? Next one. So every orthogonal set is linear independent. Here's the theory. Well, so in this topic, okay, topic 3, we have so many theories. And for those theories, we may have a proof. And you try to understand the proof. Okay, so you really need to use your noodles a lot. So how do we prove that? We say that orthogonal set. So we'll just let's create an orthogonal set. Say x1 to xk. They are orthogonal set in Rn. And then, what does that mean? Linear independent. I cannot find the coefficient, or the coefficient should be 0 if I do the linear combination for your set, right? So now, suppose I have a linear combination that vanished. So here's a linear combination. This is a 0 vector. Okay, so I don't have another vector that can be the linear combination of the rest. So now, suppose this is 0, the zero vector, then if I do the dot product with x1, what happens? If I do the dot product with x1, so x1 dot product the zero vector, the left hand side x1 dot c1 x1 c2 x2 to ck xk. The right hand side here will be c1 x1 dot product x2 x1 and c2 x1 dot product x2 and so on. So last one will be ck x1 dot product xk. What is the c1 dot c1? The norm of c1 of x1 square. x1 dot x2. They are orthogonal, or you can think about that they are perpendicular. So they have a 90 degree. So the dot product is 0. Then also others will be all 0. So this one will be only c1 norm of x1 square. The right hand side, the left hand side, x1 dot 0 vector, that'll be 0. So now they should be equal. 0 should be equal to c1 norm square. But we know that this cannot be 0, right? This cannot be 0. So only c1 could be 0. So since x1, the norm of x1 squared is not 0, this implies c1 should be 0. And if you do this for x2, x3 to xk, those coefficients should be 0. Okay.